Hello everyone, we are going to solve problem 48 of chapter 3. Determine the tension in the cables in order to support the 100 kilogram crate in the equilibrium position shown. So this crate is supported by a rope and two cables. If we want to find the forces in the cables, we need to draw the free body diagram and then write our equilibrium equation. So this is a 3D problem. So drawing the free body diagram for a 3D problem is a little bit challenging. The loads might overlap, but that's fine. That's the first step that we need to follow. So a free body diagram of ring A. I have the weight, which is 100 kilogram times 9.81. I will get 981 Newton, acting in the opposite direction of Z coordinate. Then I have my tension, TAD, and TAB, as well as TAC. So these are the four forces that are acting in our ring A. And the tension AB is along x-axis, which makes finding the Cartesian component easier, and then the component TAC is in the opposite of y-axis, so that's y. But TAD is in 3D, so I don't have the component directly from the image. I need to find the component. To write the equilibrium equations, here is 3D, so we have three equilibrium equations. Summation of forces in x, y, and z are 0. I need to find each tension or each force in a Cartesian form. So let's start with the weight. W, if I want to write it in Cartesian form, would be negative 981 K, because it's in the opposite direction of Z. And the unit is, of course, Newton. For the force TAB, I don't have the magnitude, but I have the direction. I know it's towards positive X, so TAB, the vector would be simply TABI, and TAC is in the opposite direction of Y, so TAC would be negative TACJ. For TAD, I need to find a component, but I don't have the angles, but I have the dimensions. We talked about if we have the dimensions, we can find a unit vector, and if we multiply the unit vector by the magnitude, it gives us the vector in Cartesian form. So TAD would be the magnitude of TAD that we don't have, times UAD, the unit vector from point A to point D. So my first task is to find this unit vector, so I can write all my forces in a Cartesian form. So what is a unit vector? Is the position vector divided by its magnitude. And what is the position vector? The coordinate of D minus the coordinate of A. So if I want to write UAD, the unit vector from A to D, UAD is a vector, would be the position vector from A to D. From A to D, I'm going toward 2 meter to the negative X direction, 2 meter positive Y, and then 1 meter K. I have to divide it by its magnitude to get a unit vector. And this one, 2 squared would be 4, plus 4, 1 squared would be 1, so that would be a square root of 9 would be 3. So my unit vector is negative 2, 3i, plus 2, 3j, plus 1 over 3k. So now that I have the unit vector, I can find my TAD, or I can write TAD in a Cartesian form. So TAD is simply the magnitude of TAD. I don't have it, that's why I just keep writing it like TAD, times the unit vector. So times this negative 2, 3i plus 2 third j plus 1 over 3k. So now I have all the vectors in the Cartesian form. So if I want to write equilibrium, that makes it much easier for me I will just add the x component, y component, and z component. So summation of forces in x equals 0, summation of forces in y would be 0, and summation of forces in z equals 0. This is the three equilibrium equation I have in 3-dimensional. Let's just solve by summation of forces in x. So in x I have TAB, that's the x component. TAC doesn't have any component in x, W doesn't have any component, and TAD has a component. So the two components that I have is TAB minus 2/3 of TAD equals 0. So here I have two unknowns. I can't solve it by itself. I need to go and write my summation of forces in y. If I go and look at y, TAC is in direction of y, opposite direction, so therefore negative value. Then 2/3 of TAD, and that's it. I don't have any other component. If I go to z direction, I have TAD and as well as the weight. So 1/3 of TAD minus 981, that's the weight, equals 0. So in these two equations, I had AB, AD, AC, AD. Each equation had two unknowns. I couldn't solve it. But this, the last equation, summation of forces in Z, I have only one unknown. So I can directly find TAD. So TAD would be 3 times 981, 2,943 Newton. And now that I found one of the unknowns, TAD, I can plug it into the first equation and then find TAB. And once I have TAD, again, I could plug it into the second equation and find TAC. So therefore, let me write it here. Once I have TAD, I can find TAC and TAB. So TAC would be 1,962 Newton, and TAB would be 1,962 Newton as well. They are the same, TAB and TAC. We could look at the problem and then see that, or if you look at the two equations here, TAB and TAC, both of them are going to be 2/3 of TAD. But you need to show it by equations. Never try to guess and saying that, okay, it looks like TAB and TAC are the same. That won't be acceptable. You always need to show how you come to that conclusion. So in this problem, the two tensions were in x and y axis, towards x and y axis, so that was very simple to write it in Cartesian form. But the force TAD was in 3D, and first we had to write it in Cartesian form, and once we have in Cartesian form, then simply for summation of forces in x, we just add the x component. For y, we add the y component, and for z, we added the z component, and all of them should be equal to 0. Then we will find the unknown.